The condition for a circular orbit is that the centripetal force is equal to the gravitational force. Centripetal force on each orbiting object. Remember, two objects that orbit in an isolated system. Now this is circular orbit of an isolated system, in a system where you don't have any unequal forces acting from some other source. You have this, the centripetal force that keeps each object in a circle around the center of mass is equal to the gravitational force between the two objects. So that you have mv squared over r, the centripetal force at distance r, equal to g, universal gravitational constant, times little m times big M over the square of r. Now, we're given a problem in which we're asked to find the mass of a planet about which a satellite is orbiting at a given rate. Okay? And we're not given the velocity of the object, we are given the radius of the orbit, okay, the distance of the satellite from the center of mass of the planet. Now, when you have a satellite and a planet, a small satellite and a planet, the center of mass is really biased toward the center of the planet, so much so that you regard the radius of the orbit as the distance from the center of the planet. For a 1,000 kilogram spacecraft, about a typical planet, the center of mass is probably within a couple of millimeters of the center of the planet. So you're not making any mistake by letting r be the distance of the satellite from the center of the planet. The satellite has a mass that's more appreciable compared to the planet, like a moon around a planet, then you do have to worry about the position of the center of mass. For example, between the Earth and the Moon, the center of mass of the Earth-Moon system is not at the center of the Earth. It's within the Earth. It's not too far under the crust of the Earth, not too far beneath the surface, but it's not at the center of the Earth. So the Earth is actually moving a little bit about that center of mass as the Moon moves around the Earth. Okay, well, digression aside, okay, what you're given is the time it takes to complete a circuit, to complete an orbit, and the radius of the orbit. From those two things, well, you know the radius of the orbit, so you know r, and from the radius of the orbit and the time it takes to complete an orbit, you can calculate v. You also know the universal gravitational constant, and you have little m on both sides of the equation, meaning that once you've calculated v, you can solve for big M. Okay, well, okay. So, big M is v squared r over g. We need to find v. Okay, well, we use the definition of pi to find how far you go along the path of one orbit, because we know the time it takes. Okay, so, and then we divide that by the time it takes to make an orbit, and we get a velocity of approximately 140,000 meters per second. Okay, that's pretty good velocity. And I comment we get that from the distance we move along the path is 2 pi times the radius, the circumference, and the delta t is 4 hours. So you just plug in what you have, and I believe you get this velocity. Okay? And from that, and the given radius, we easily calculate the mass, find that it's about 8 times 10 to the 28th kilograms. Now that's a very massive planet. That's about 10 times the mass of Jupiter, and the order of magnitude greater than the mass of Jupiter. And you're getting into the realm where that mass would tend to collapse on itself, ignite, and form a star. Okay? And without going into the details of that, I'm not sure exactly where that most tends to happen. But you're getting into the lower range of star mass This is about maybe mass of the sun. I'm thinking about a 40th the mass of the sun. I don't remember what the mass of the sun is. Maybe a 50th, maybe a 30th. So pretty massive. In any case, that's how he solved the problem. Once you have the law of universal gravitation and understand what it takes to make a circular orbit, this is a relatively simple calculation. Now the next thing we want to talk about is how to figure out the work that would have to be done to essentially raise something from the surface of the Earth at 6,350 kilometers from the center to a point that's 450 kilometers above the surface of the Earth. So if we wanted to take a kilogram and raise it to an altitude of 450 kilometers, how much energy would we need? How much work would we have to do? Now we're given the mass of the Earth, okay, and we know the form of the universal law of gravitation, Newton's law of universal gravitation. So we're going to be able to figure this out, but the kicker is that the force on that 1 kilogram is going to diminish as we get further from the center of the Earth, because our distance from the center of the Earth, which is r here, is going to be getting bigger. So we have to figure out how to form an integral. Okay, so we're going to do that in the next video.